Haber process is an industrial method of ammonia production through the reaction of nitrogen and hydrogen gas. It was discovered by Fritz Haber around 1913 and later developed by Carl Bosch. The main product, ammonia, is considered to be a vital part of nowadays life, as it serves as an important component of agricultural fertilization that is based on the nitrogen. A prime example could be urea and ammonium nitrate, Salanki 2023. To prove ammonia's significant position in human lives, according to ThyssenKrupp, no date, 80% of a produced ammonia is used for product fertilization annually. This depicts the great contribution of this chemical to our dietary activity. Food production is almost entirely dependent on ammonium, as the human population is growing every year, which will require a faster harvest. Moreover, it was concluded that 50% of the population is fed with the help of ammonia, Erisman et al. 2008. This means that without this chemical, there would be hunger and higher mortality in the many countries, especially in places where the soil is not fertile enough, as there wouldn't be enough food for the growing population. And the past alternatives like animal manure or guano wouldn't have been so useful for maintaining well-being.
The chemical equation for the Haber process is N2 plus 3H2 produces 2NH3, where nitrogen gas and hydrogen gas react to produce ammonia. According to StudyMind, no date, the reaction in the Haber process generates heat, meaning that it is exothermic. The reaction is also reversible because ammonia can form hydrogen and nitrogen gases and the other way around. The Haber process can be broken down into 5 steps, as described in an article by StudyMind, no date. First, hydrogen and nitrogen gases enter the reactor. Second, they go through an iron catalyst, which will help speed up the reaction, while 450 degrees Celsius temperature and 200 atmosphere pressure are applied. Third, the reaction occurs and ammonia is produced. However, not all of the reactants are used. Fourth, the mixture of nitrogen, hydrogen, and ammonia goes into the condenser, where they are cooled down. Because ammonia has a lower boiling point, it condenses into a liquid, while the other 2 gases do not. And fifth, liquefied ammonia is collected at the bottom, while nitrogen and hydrogen gases go back to the reactor. For the Haber process to run smoothly, there are some conditions that have to be met. The first one is related to temperature. According to Le Chatelier's principle, the exothermic side of a reaction is favored at lower temperatures. However, lower temperatures also slow down the rate of reaction. Thus, the temperature chosen for the Haber process is around 450 degrees Celsius, as it is low enough to produce a decent amount of ammonia and high enough to not prolong the reaction. BBC, no date. The second condition is the amount of pressure. Using graph 1 and the same principle from before, it can be known that at higher pressure, the reaction favors the side with fewer moles of gas, which in this case is ammonia. As well as that, higher pressure leads to a quicker rate of reaction. Nevertheless, the optimal pressure for the Haber process is set at approximately 200 atmospheres. The main reason for that is the high cost of achieving higher pressure, as the machinery is expensive and a lot of energy is required. StudyMind, no date. Apart from that, high pressure in industrial settings can lead to equipment failure, explosions, and potential harm to workers. Aaron, no date. The last condition is a catalyst. They do not have an effect on the amount of ammonia that gets produced, but they do increase the rate of reaction. In the Haber process, iron is used as a catalyst because it is cheap and helps to speed up the reaction. Now that the main conditions for the Haber process are established, what needs to be considered are the raw materials used for this reaction. One of the 2 main reactants is nitrogen gas. According to the School for Excellence in 2019, fractional distillation is used on cold and liquefied air to acquire nitrogen for the Haber process. The source is air because it is composed of about 78% nitrogen. National Oceanic and Atmospheric Administration, 2024. The second main reactant is hydrogen gas. It is mainly produced through a process called steam methane reforming, which can be expressed as CH4 plus H2O plus heat produce CO plus 3H2. In that process, a methane source like natural gas reacts with steam, producing hydrogen, carbon monoxide, and a small amount of carbon dioxide. US Department of Energy, no date. After that, through a water-gas shift reaction, the carbon monoxide and steam react to produce an additional amount of hydrogen, CO plus H2O produce CO2 plus H2.
The Haber process has its own advantages and disadvantages, which we evaluated according to two factors: economic factor and environmental factor. Economic factor advantage: lower food costs. Ammonium helps produce more crops for less land. As the quantity of food increases, the price of it decreases, thereby making it more affordable and profitable for the population. Second, increased food population. According to Jean et al., in 2019, the production of ammonia has resulted in an increase in the food production by 7-8 times since the beginning of the 20th century. That is because ammonia is present in the nitrogen-based fertilizers, which improve soil fertility and help provide larger harvests. Disadvantage: energy dependency. The Haber process relies on fossil fuels, such as natural gas, for hydrogen production. This makes it require more energy and depend on the fluctuations in the energy prices, which can increase the production costs. Environmental factor advantages. First one is fertile soil. Ammonium helps the earth become more fertile for large harvests, as well as make insufficiently fertile land fertile, thereby providing people with the food. For example, the Haber process is widely used in India, as despite the presence of natural resources, they number more than 1 billion people. Most of the country's population depends on chemical additives, including ammonium, and without them, their harvest would be significantly reduced. Second one is maximum land use. Ammonium allowed the use of less land for a large harvest, which will lead to the conscious use of land for food. Disadvantage: environmental pollution. Excessive use of ammonium often leads to negative consequences such as nitrogen and carbon pollution. It releases nitrates runoff that could potentially cause water contamination, eutrophication, and harm to aquatic ecosystems. In conclusion, in the future, the Haber process will be more efficient and greener because of the development of new waste and catalysts. Using green hydrogen manufactured from renewable energy sources and more efficient catalysts currently under development by researchers can reduce the energy demand for ammonia production. This can reduce the cost of production, hence the fertilizers produced may become cheaper to enhance food security, especially in developing countries. Changing methods of ammonia production will go a long way toward reducing greenhouse gas emissions and, by extension, mitigating eutrophication from fertilizer runoff. It will no doubt remain one of the most important elements in the feeding of the ever-growing global population, but this time in a more sustainable manner, economically diversified, to ensure a long-term benefit to both the environment and the economy.